Hello everyone, welcome to this session. So in this session, we will introduce normalization, standardization, and power transform. So first of all, what is normalization and standardization? So what is the goal of them? The goal is to make the data of the each dimension to be similar, right? So why we need them? Because in reality, different data have different types, right? So for example, a person's height and his weight. So if we say height, let's use maybe use meter as a unit. Then we say 1.7 meters. And if we say the weight maybe 65 kilograms, so 1.7 and 56, these ones are quite different, right? So if we use some machine learning method that use distance, so for example kn, then the weight will dominate the distance. So this is not good for the machine learning method. So that's why we want to make them similar, right? Make the different the types of data to become the value become similar, so as to make the machine learning method works well. Then that's why we need normalization and standardization. So normalization is for the non-Gaussian distributed data, while the standardization is for the Gaussian distributed one. So let's see the normalization first. So for non-Gaussian distributed data, normally we want to make all of the data between 0 and 1 or minus 1 and 1. So let's see one from to normalize all the data between 0 and 1. So this is the formula. X minus x mean, and here is x max minus x mean. So we can find that when x equals to the smallest one, x mean, the normalization value is 0. So here y is max, this value is 1, right? So all the other data are between them. So all of the data goes to 0 and 1. So we can see here, these are the data of a different range, but after normalization, both of them goes to 0 and 1. So you can see the live script for more details. So normalization is for non-Gaussian distributed data. So if we go to the Gaussian distributed data, we call it standardization. So what is the formula? We can see is here. Yeah, right. So what is this? This is a z-score, right? Z-score. So z-score will make a Gaussian distributed data from with any mu, the average, and the standard deviation to the 0 as the average, and the standard deviation is 1. So by using this formula, we can change any Gaussian distributed data to this one. We call it a standard Gaussian distributed data. So the character is mean 0 and the standard deviation is 1. So you can also see the live script for more details. So some data have a strong skewness, right? So then in this case, we can use a power transform to remove the skewness. So what can we do is a power transform is not a single method, but is a series of methods, that called a family of data transformation techniques using power functions. And these functions is monotonic. So we can say it's like fx equals to axp. So this is power function. So by power transform, we can see this one has a high skewness, right? So after the power transform, we can see it's more Gaussian-like, right? So what are the benefits of the power transform? First, we remove the skew. In a more formal saying, we can say we stabilize the variance of the data, but these two sayings are of the same meaning. And this one by doing this, we can remove the impact of the extreme values. And also, we make the variance be more consistent across different regions. And also by doing the power transform, we can generate more Gaussian-like data. So the many machine learning models, they works well on the Gaussian-like data. So now let's see an example of the power transform. We call it the Box-Cox transform. the box Cox transform that the formula is here. So the y0, this is the original value. Following this formula, the lambda here, this is we call it the power parameter. So this power parameter is estimated by the log likelihood function or by the profile likelihood function. So this is estimated a number, and are using these formulas with lambda, the transformed values here. So we can see an example for this one. We go through the box Cox transform, becomes a more Gaussian-like method, and the skewness is removed. And then we can do the inverse transform by following these formulas, right? Okay. So next, we can see how to implement the box Cox transform. So we can use a built-in function called box Cox, input the original data. Then we can get two outputs. This is the transform data, and this is the estimated lambda. So we get the related function. You can check in the MATLAB help file, so here, and as well as this function, if for inverse. So if we use the box Cox transform, we can generate this. So if we use this function to get the inverse one, we can make it back. So more details in the live script, and you can see it. And so in this session, we talk about the normalization, standardization, and the power transform. So power transform have other methods. For example, the Johnson transform. This is also widely used, and I don't cover in this introductory course. But if you are interested, you can learn it yourself by searching via the internet, right? And for the data standardization, normalization, and power transform, so we all want to, the goal is the same. We want to build a data set that is suitable for many machine learning methods. So for some machine learning methods, it doesn't need to do the normalization or standardization or power transform because it's not sensitive to that. But as a general practice, so we hope you to do it before applying for the machine learning algorithms, just as a general practice. So that's all for this session. Thank you very much. Bye-bye.